Right, Assalamu alaikum. So in the year 1923, when Compton first reported the results of his experiments and established that X-ray photons can have momentum and they act like particles, it was in the same year that two American scientists, Davisson and Germer, in the United States, and G.P. Thomson in England, they established the wave nature of electrons. So it's very surprising that the father of G.P. Thomson, whose name was J.J. Thomson, established the particle nature of electrons, and the son established the wave nature of electrons. So you must remember that we looked at a modern version of J.J. Thomson's experiment in the classroom, in which we deflected electron beams using magnets. So there's quite a conflict in the family in that sense, that the father was proposing the particle nature and the son was proposing the wave nature. But now that we have seen the double slit interference pattern, we now have a fair idea of what the electron really is, and we've introduced the concept of the field psi, which is an overarching concept which holds both the particle and the wave nature together. So, but let's first have a quick look at Davisson and Germer's experiment. So their experiment was in fact quite a beautiful exposition of experimental skill. Shall I please settle down? So Davisson and Germer's discovery of the wave nature of electrons was a fortunate accident. The experiment looked like the following. They had a giant bell jar The bell jar could be evacuated. So this goes to the vacuum pump. Here they place a crystal of nickel . This is a nickel crystal. They have an electron gun, which is simply a filament with a variable voltage source. And a voltmeter that can measure this voltage. Of course, there are slits which produce a fine beam of electrons. So here are electrons that are falling onto the nickel crystal. And in between, one can apply a potential difference. So between this plate and this plate, one is able to apply a potential difference. This is positively charged, it attracts the electrons. This is negatively charged, and one produces a voltage across these, which is also measurable and variable. Okay, so this is an accelerating potential for the electrons. The electrons come out of the filament, the current can be measured through the filament, the electrons come out, they are accelerated and they strike the nickel target. Now these electrons, they are scattered, they are reflected from the surface of the nickel and they have to be detected. So these electrons are scattered in a certain direction, and when they are scattered they must be detected with some kind of mechanism. For example, they can have a detector for electrons. And this detector can vary its position along an arc. So this is the experimental arrangement. Okay, so what Davisson and Germer were trying to do, they were trying to investigate how electrons interact with the surface of the nickel crystal. So what happened in the experiment is that somehow this glass vessel broke. Something dropped on this glass vessel, it broke, and when it broke, the vacuum was destroyed. Air rushed in and the vacuum was destroyed. Now this nickel was placed on a small heater. This is a heater. And the nickel was at a high temperature. So when air rushed into the glass vessel, the nickel was at a high temperature, nickel got oxidized. Okay, so this nickel reacted with oxygen to form nickel oxide. So a layer of oxide was formed on the nickel surface, and now Davisson and Germer thought that they had to get rid of this nickel oxide and they had to mend the apparatus. So what they did was they kept on heating the nickel oxide that was formed and very slowly passed hydrogen gas through the apparatus. And when they passed hydrogen gas through the apparatus, the nickel oxide was reduced. Very slow passage of hydrogen, the nickel oxide is at a high temperature, and one recovers nickel and water vapors which go out of the system. So this is how they would like to recover the nickel from the nickel oxide, by reducing the oxide back to nickel. Now what they observed inadvertently, by mistake, was a beautiful result that would change our perception of the electron forever. Now what happens is that if you have a metal such as nickel, now this is a crystal. A crystal means that all the atoms are in regular planes, very regular planes. These are the nickel atoms in regular planes. Everything is periodic, orderly, pristine. This is how we define a crystal. Every solid has a crystalline structure. Most solids have crystalline structures. But if you look at the material as a whole, one region will have planes in this orientation. If this is your total sample, this is one region inside the sample in which everything is orderly and perfect. This is a pure crystal. In the neighboring region, there is a sudden change in the orientation of the planes. So here the planes change their orientation. It's orderly inside this region, but this region is different from this region. Here there is another region which is orderly in itself, in its own right, but differs from neighboring regions. Here you might have a different orientation. So this is what a real solid looks like in real life. These regions are called grains. So this solid has multiple grains in it. Now when Davisson and Germer were reducing the nickel oxide and producing nickel, they were slowly passing hydrogen gas and they were constantly heating the nickel crystal. So when you slowly heat a crystal, very slowly, what happens is that one of the grain grows in size and the other grains shrink. So if you slowly heat this material, what you will observe is that one of the grain, for example, this grain is growing, and this is the orientation of the planes, while the other grains are steadily shrinking. And if you keep on heating slowly, eventually all of this solid will become one grain. So all of the solid will become one grain. This is called a single crystal. And this process of slow heating is called annealing. So when Davisson and Germer were reducing the nickel oxide, they were slowly heating the material. Nickel was being formed, a crystal of nickel was being formed, and since the heating was very slow, the process of annealing took place, and eventually after some time they obtained a single crystal of nickel. Okay? This multi-grain structure, this polycrystalline structure, collapsed into the favor of a single crystal structure, just one grain, one orientation of planes. Now let's see what happens when electrons fall onto such a structure. This is very similar to X-ray diffraction now. Suppose you have a plane of atoms and electrons come in, strike the plane of atoms. These electrons are coming in as a parallel beam. Conventionally, these electrons were thought to be particles by virtue of J.J. Thomson's experiment. Okay. Now these are low energy electrons, so they cannot penetrate into the sample. What will happen is that these electrons will be scattered. And the scattering will appear as if reflection is taking place from the top plane. Now if this angle, which is the conventional angle of incidence, is theta, the angle of reflection is also theta. And here's a detector, an electron detector. And now this is a plane of atoms. So the plane of atoms goes like this as well. Okay? So the spacing between this plane and this plane is given by D. Now what happened is that if the angle of incidence and the angle of reflection theta was changed, the intensity of the detected electrons also changed. And there was a certain angle theta at which the intensity was maximum. So what is happening here is that these incoming stream of electrons are acting like waves, and when they are scattered off from different regions of the top layer, they interfere with one another. And when they interfere in such a way that constructive interference has to take place, the intensity that is measured by the detector is maximized. Now from this arrangement, can you tell me what the path difference between the waves should be? What's the path difference between waves 1 and 2? Can you please calculate this for me? वो जो रे 1 और 2 मैंने दिखाई है उनके दरमियान फेज डिफरेंस क्या होगा? Sin theta, which you remember from the Bragg's result, is incorrect. Use your mind, not your brain. Choose points on rays 1 and 2 that are in phase. It's not D. So ray 1 and ray 2 are emerging from the top layer. I draw a normal from ray 2 to ray 1. This is 90 degrees. Now this point P and this point is Q. Rays that start from Q and rays that start from P have traveled the same distance in reaching the detector. So the additional distance ray 1 has traveled is RQ. We have to find what this distance is. Okay? Now if this angle is theta, then This is 90, this is 90 degrees, this is 90 degrees, this angle is theta. So if this angle is theta, this angle is also theta, okay, but this angle is 90 degrees, so this angle is 90 minus theta, so this angle has to be theta. If this angle is theta, this reflection angle is also theta, but this total angle is 90, so this angle is 90 minus theta, this angle therefore is theta. So if this distance is d, then what's this distance, RQ? It's d sine theta. Okay? If I were to define this angle as theta, then this would become d cosine theta. So it depends upon how I define theta. Here I have defined theta in this manner. So what happens in the Davisson-Germer experiment is that this d is given by this is d sine theta when this equals lambda, which is the wavelength of the electrons. Constructive interference takes place. And what is this lambda? This lambda is given by h over mv. Since these are low energy electrons, we can apply the non-relativistic expression. Okay? Now what is the velocity of the electrons? That can be determined simply by half mv squared equals capital VE or V naught E, where V naught is this potential. Okay? So V turns out to be 2 V naught E over M under root, and lambda becomes H over M into M over 2 V naught E. So everything is known here. V naught is known, the charge on electron, the mass of an electron, or the charge to mass ratio of an electron is known. One can determine lambda, and from that one can determine the angle at which maximum reflection takes place, at which the intensity of the reflected ray is maximum. The value of d for the crystal is also known. So this experiment helped Davisson and Germer establish that these electrons indeed have a wavelength, although they are particles conventionally, but here they are acting like waves because they are being diffracted, they are being scattered, and these waves are constructively or destructively interfering. So this was one of the first experiments that highlighted that electrons can really act like waves. So what we have now is something very interesting. Let's gather up all our thoughts. We've seen that matter acts like particles and light acts like waves. Electrons act like particles, they act like waves. Photons act like particles, photons act like waves. Protons, neutrons, most of the small objects, the subatomic particles, they act like particles and they act like waves. So we introduce this overarching concept, this big concept, what we call the field or the wave function. Psi, which exists with every object, and this fills up all of space, all of the energy of the object is smeared out in space. This object acts like a wave, it can be diffracted, and when it is detected, this object has all of its energy gathered together and falls onto a detector, and it starts acting like a particle. That is what we call a particle. Now, and these are also called matter waves, of course. So instead of focusing on particles and waves separately, we can just focus on psi, or the field, or the wave function. And that is what we are going to do. But first of all, let's have a look at the uncertainty principle in light of the definition of psi. Now this is something you must really understand very well. I am spending elaborately more time on these concepts because these are the most difficult concepts, the most subtle concepts, and these are the concepts that you should remember in your lives hereafter, for all your lives. Now I draw a wave function psi. Okay? And this carries on. This extends to this side as well. So this is a wave function that I choose to draw. Okay? And this axis is x. It's space. Okay. Now if I look at this wave function or field, first of all, let me tell you that this wave function may represent an electron that is traveling in a straight line. But when you see this electron traveling in a straight line, you notice that first the electron is here, then it starts moving, and it has a trajectory, it has a certain velocity, it keeps on moving and goes from your left to right. It has a trajectory. But this picture does not show this trajectory directly, because this picture is drawn in all of space and it's drawn at all times, which means that when we consider the electron or any particle to be a field, the concept of time is very tricky, and this field instantly fills up all of space. Okay? I mean, the particle does indeed have a trajectory, it does have a velocity, but when you think of it as a field, this field immediately fills up all of space. And this is something we learned from the delayed choice experiment as well. Because if you think of the particle as moving from your left to the right, it has a course of action. And what happened in the past determines what happens in the present, but what happens in the present cannot determine what happened in the past. So there is an arrow of time. But in this field concept, there is no arrow of time. As soon as you think of this electron that is moving, there is a field associated with it that fills up all of space instantaneously. Okay? It's a ghostly field that fills up all of space. Now if you look at this wave function that I've drawn, does it have a wavelength associated with it? Yes. This is the wavelength of the field, and loosely we say that this is the wavelength of the electron. But remember, again I'm emphasizing this, that this wave function does not mean that the electron is moving on this trajectory. The electron is still moving in a straight line perhaps. Okay? So we can think of a wavelength. Now we know from the de Broglie relationship that P, the momentum of this electron, is related to the wavelength h over lambda. So I can write this as h over 2 pi over lambda h bar k. So do I know the value of k? Yes, because I know lambda. Do I precisely know lambda? Yes. I precisely know what the wavelength is. By looking at this hypothetical wave function, I precisely know what the wavelength is. Therefore, I precisely know what the k value is. I precisely therefore know what the momentum of this particle is. Okay? Therefore, I also know what the speed of this particle is, because I know its mass. Okay? So, I really do know what the wavelength or the momentum of this particle is. Now the question is, do I know the position of the particle? Now this is the wave function of the particle called the electron. देखो अब पार्टिकल और पार्टिकल का लफ्ज आप कुछ उसे शक की निगाह से देखना चाहिए आपको, ठीक है? जब मैं कहता हूं ना पार्टिकल इलेक्ट्रॉन, ये तो पार्टिकल तो नहीं लग रहा, लेकिन पार्टिकल sticks to our vocabulary in such a way that we often keep on using this word. So now we have the electron, the particle electron, which is described by this field. Quantum mechanics tells you that all you need to tell everything about the electron is just draw the field. ये आपकी पूरी शनाख्त है, इलेक्ट्रॉन की पूरी शनाख्त इसके अंदर है, ठीक है? जिस तरह डीएनए के अंदर, जीनोम के अंदर किसी भी इंसान की या जानवर की या पौधे की पूरी शनाख्त है, इसी तरह पूरी शनाख्त किसी भी पार्टिकल की इस वेव फंक्शन के अंदर है, इस फील्ड के अंदर है. अच्छा, now the question is, if I would like to ask the question, where is the electron? It's a very legitimate question to ask in physics. Where is something? I ask, where is the electron? Now how do I answer this question? I cannot give a definite answer. Suppose I don't look at the electron, I don't make an observation, I don't make a measurement, then I cannot answer this question, where is the electron? But if I just look at the field, I can tell that the electron can be anywhere. How do I know that? What I would do, I would take the modulus square of this field. Now this field, this is the axis. So half of the wave function is above, it's positive, half of the wave function is negative. Now I draw another axis. And I draw psi mod squared. Now this is a plot of psi mod square. Now this is the probability density. The electron, if this is psi mod square, the electron has a large range of possibilities for where its position can be found. Okay? So the electron can be found at any point along this axis, barring or except these points. It cannot be found at these points. These are forbidden points because the probability density is 0 here, 0 here, 0 here, 0 here. Now if I would like to make an observation and I would like to answer the question, where is the electron, I would need to have some kind of detector. Okay? So there are two kinds of detectors. I can have a small detector which is just placed here, and if I have one electron, there is a certain probability that this electron will click or it will not click. ये बात बड़ी तवज्जो से सुने. अली थोड़ा सा उसको कहें कि ये ऊंचा कर दे. So one possibility is to have a small detector. पीछे बातें ना करें. ये कौन समझाएगा फिर आपको? ये समझ आ चुकी है आपको? If you have a small detector which has a small field of view, a small range, and you just have one electron in space with this wave function, there is a probability that this electron will click and there is a probability that it will not click, and that probability is proportional to the value of psi mod square at this point, or it's proportional to this area. The other possibility is that I have a camera. I have a camera that takes a picture of the electron, and the camera can see the entire span of the electron. The screen of the camera is the entire blackboard. So the single electron can click anywhere. It can click here, 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 anywhere besides these nodal points. So that single electron can click anywhere. Okay? So once it has clicked, suppose it clicks here at x naught. Now this electron clicks at x naught. Can you say, first question, can you say that the electron existed at x naught when I made the click?
Yes.
So now you are detecting the electron, you're making an observation, and you detect the electron to be present at x naught. But if you look at the wave function, you cannot say with certainty that the electron was present at x naught, hence you detected it to be at x naught, because the electron could have existed anywhere. You don't understand? Okay. Suppose you detect this electron to exist at x naught. Okay? Now another electron, and now you have the camera. First you have the camera, and you measured the electron to exist at x naught. You measured this position. Now you have the camera. An identical electron is fired, is launched, which has the same wave function, and you have an identical camera, and you make an identical observation. Okay? Your consciousness in your brain is identical to his. The camera is identical, it's the same model. In fact, you share your camera, you give your camera to him. It's the same camera, identical conditions. What will you detect? Will you detect the electron to be at the same x naught? Classically, yes, because everything is identical. The electron is identical, the time at which you make a measurement is identical. But no, you will detect the same electron to exist somewhere else. You might make an observation that the electron exists here. In fact, you will make a different observation. It's very likely that you will make a different observation. So now you say that the electron exists at x naught. I've seen the electron at x naught. therefore the electron must be at x naught. You say that I've seen the electron at x1, therefore the electron must be at x1. So there's a conflict. आपने अपनी आंखों से देख लिया कि इलेक्ट्रॉन x नॉट पर, आप तो कहेंगे कि the electron had this position x नॉट, आप कहेंगे the electron had this position x1, लेकिन हकीकत में ऐसा नहीं है. The electron, you cannot say that the electron existed at x naught, hence I detected it to be at x naught. Neither can you say that the electron existed at x1, therefore I detected it to be at x1. What this wave function is telling us, that the electron's position has a realm of possibilities. एक मिनट में सिर्फ बात खत्म कर लूं. रियल्म का मतलब पता है क्या मतलब इसका? There is a range of possibilities. एक वसी इम्कानात की गुंजाइश है. इलेक्ट्रॉन की पोजीशन has a realm of possibilities. There is a range of possibilities. Because this is a possibility curve or a probability curve. So the electron can exist. It does not exist at one point. Once you measure it, there is a realm of possibilities of what you can measure. In other words, you would say that the position x is uncertain. So this is slightly confusing because uncertain is a negative word. Uncertain एक negative word है. Possibilities is a positive word. ठीक है, किसी चीज के अंदर potential होना, to exist in a wide range of space is a positive word. It's a positive attribute psychologically. The word uncertain is negative, but this is what physics gives. This word is given to you by physics, by Heisenberg, the uncertainty, but really it means a realm of possibilities. So now for this particular object, if I were to draw a curve or a graph, this axis is x and this axis is p. Before I have made the measurement, just by looking at the wave function, x is totally uncertain. But what about the momentum? Is there a realm of possibilities for the momentum as well? No, it's totally certain. Okay, so there's a realm of possibilities for x, but the momentum is totally certain. You certainly know what the momentum is. When you measure, when these two gentlemen measure the momentum by some apparatus, they will get exactly the same value. But remember, those have to be different electrons that you measure. Because once you measure the electron, you're going to disturb its wave function. This wave function will no longer exist, because this wave function is going to collapse. So you need an identical copy or a clone of the same electron to perform an experiment. Okay?
Aren't all electrons belong to each other?
Yes, but you need identical instruments, you need identical detectors. Just 1 minute, I have 2 questions to answer, so I'll do that. So if I were to plot, before I make an observation on this graph, the realm of possibilities, can you please give me a plot of a line or a circle or a region which I should plot on this curve? It's going to be a horizontal line on this curve, because X has a wide realm of possibilities, an infinite realm of possibilities, but P is totally certain at some point P naught. Okay? So what, in terms of physics, we have to do a little bit of physics as well, not just pictures, but delta X is the uncertainty in X. This approaches infinity in this case, it's very large, and delta P approaches 0. Now this is the state of affairs before the measurement. I would like to plot the state of affairs after the measurement. First of all, I would like to plot the wave function which I obtain when I make an observation. आपको मेरी आवाज ठीक आ रही है? क्योंकि मुझे बहुत ऊंचा बोलना पड़ रहा है. आप तसल्ली रखें, मैं आपके जवाबात भी दूंगा. Suppose your camera measures the electron to exist at x naught. Okay? So what is the new wave function? This wave function is going to collapse. Whenever we make an observation, the wave function collapses. And this means that a new wave function is created. A new particle is created, a new wave function is created, a new identity is created. So the act of observation creates a new object with a different wave function. Anything that has a different wave function is a different object, as far as physics is concerned, as far as quantum mechanics is concerned. A new wave function is created. Now you definitely observe the electron to exist at x naught. Even though it existed everywhere, it had the potentiality of showing its appearance anywhere. Okay? It had the potentiality, the probability, the possibility of showing anywhere it wanted. But you observed it to be, you trapped it at x naught. You trapped it at x naught, which means that the wave function collapses into a new wave function. A new wave function is created. The old wave function disappears. ठीक है? पुरानी दुनिया खत्म हो गई और एक नई दुनिया बन गई जब आपने ऑब्जर्वेशन की. इस तरह फानी कहता है, हर नफस उम्रे गुज़श्ता की है मैयत फानी, जिंदगी नाम है मर मर के जिए जाने का. कि जो आप जो भी सांस लेते हैं, कि आप जो भी सांस लेते हैं वो आपकी पिछली पुरानी जिंदगी की मैयत होता है. तो आप पुराना वेव फंक्शन बिल्कुल खत्म हो गया, मर गया. अब आपने नया वेव फंक्शन पैदा किया और नया वेव फंक्शन इस तरह का होगा. ये नया वेव फंक्शन है क्योंकि you have definitely observed with your own mortal eyes that the position of the electron as given to you, as told to you by your detector, is x naught. Therefore your position is x naught. So this is your new wave function. And if your detector, no camera is perfect, it will have some uncertainty. So your wave function will actually be slightly spread out around x0, like this. This is your new wave function after the collapse of the old wave function. Now can you precisely tell what the position of this particle is, what the position of this particle is? Yes, because it's localized around x0. So this is a localized in space. But can you tell what the momentum of this wave function is? You cannot tell what the momentum of this wave function is, because the momentum is spread out. ये मैं अभी थोड़ा सा दोबारा, remember Fourier integrals? Something that squeezes in x has to spread out in k. Something that squeezes in k has to spread out in x. So you don't know the momentum of this particle. There is a realm of possibilities for the momentum for this wave function. The momentum becomes totally uncertain, but the position is certain. So after measurement, if I would like to plot what is happening on this space momentum curve, what will I plot? I will plot a vertical line. In fact, a slightly smeared out line. Slightly smeared out, because this is not a sharp peak, this is smeared out. मुश्किल अंग्रेजी के बगैर फिजिक्स भी नहीं होती. And what's the location of this point? x0. So after measurement, your delta x approaches 0 and your delta p approaches infinity. So position and momentum, they are conjugate variables. They are like a seesaw. पोजीशन में अनसर्टेनिटी बढ़ेगी, मोमेंटम में कम हो जाएगी, कम हो सकती है. मोमेंटम में कम होगी, पोजीशन में अनसर्टेनिटी बढ़नी जरूरी है. इन अदर वर्ड्स, डेल्टा एक्स, डेल्टा पी has to be greater than some constant, and that constant is h bar. And in wave motion, we discovered the same result. We discovered delta x, delta k has to be greater than some constant. Suppose that constant is 1. Some constant of the order of 1. So if I take this result that we derived from the wave theory, from the concept of Fourier integral, if I multiply this with h bar, I multiply this with h bar, this h bar delta k is delta p. So this relationship, which is called Heisenberg's uncertainty principle, is really nothing that is just unique to quantum mechanics. It comes out of wave motion. ठीक है, बुरहान चुप करके बैठो, बुरहान से आगे जो बैठे हैं वो भी खामोशी से बैठे. ठीक है, तो हाइजेनबर्ग अनसर्टेनिटी रिलेशनशिप इस चीज का नाम है. This is nothing unique to quantum mechanics. Whenever you have a wave, you will have this kind of property. That is, momentum and position will be inversely related, and the uncertainty is actually related to the realm of possibilities. Now I am happy to take 3 or 4 questions. सबसे पहले आप पूछें.
Sir, you say that the electron exists in realm of possibilities. So when the detector just time, doesn't it exist at that particular space in that time?
देखो अब आप प्लीज खड़े होके ये सवाल उनसे पूछें, बाकियों से पूछें, क्योंकि ये सवाल इतना अहम है कि सब लोगों को सुनना चाहिए। इन्होंने ये सवाल पूछा है कि अगर मैं इलेक्ट्रॉन को पोजीशन x0 पर डिटेक्ट करता हूं इन माय मेजरमेंट, डजंट इट मीन दैट द इलेक्ट्रॉन exists at x0? It had existed at x0, so it's moving everywhere and you trap it at x0. ये मतलब है ना आपका तो कि it's moving everywhere quickly, very fast, it's moving very fast and then you trap it at x0. पकड़ लिया उसको, यही मतलब है आपकी बात का। लेकिन ऐसा नहीं होता, क्योंकि मैं आपसे एक सवाल पूछता हूं। लुक एट दिस लोब ऑफ द पॉसिबिलिटी कर्व, ठीक है? लुक एट दिस लोब ऑफ द पॉसिबिलिटी कर्व. व्हाट्स इन द मिडल ऑफ दीज लोब्स? The electron will never be found here. So if an electron is actually jumping from this location to this location, Greek philosophy tells you that there must come a time when you trap the electron here, when you detect the electron here, because the electron is not a ghost. It cannot pass through the wall without being seen in the wall. It has to pass through this transit point. This is a transit point for the electron, if the electron is really moving from here to here. But the electron can never be found here. So this means that your question is not on the correct premises. It is not legitimate to ask this question in quantum mechanics. It is legitimate to ask this question in classical physics, because we think of an electron as an object in transit. It's an object in motion. And therefore, since it is in motion, in order to go from left to right, it must pass through all points in between. This is called the famous Zeno's paradox. The electron has to pass through this point, but you never find the electron here, which means that the electron is actually not passing. The electron is actually not moving. The electron is actually not transporting from one region to another. It's not locomoting. Stop thinking of the electron as an object in motion. The electron is a field, and that is the only way which can satiate your ego. That's the only way which can satisfy you. You can think not of the electron as a particle in motion. Think of it as a wave or a field or a wave function that is smeared out in space, which has a realm of possibilities of being detected, and once you measure it, you collapse it into a certain state. Muhammad Awais. Every electron is identical to any other electron. However, when you perform a quantum experiment, identicality means everything else has to be identical. Because as we observed the other day, if you place a detector at one location, it gives you a different result. You place a detector somewhere else, it gives you a different result. You place a detector or no detector, it gives you a different result. So the observation is a part of the object itself. The observation, the measurement, the detection, the environment, everything has to be identical. The timing, everything has to be identical. And by an identical electron, I really mean an identical experiment. ठीक है? आप पूछें.
Once the electron is detected,
ये देखो प्लीज, ये सब लोग सवाल भी सुने. सवाल भी उतना अहम है जितना जवाब है, बल्कि सवाल ज्यादा अहम है.
Sir, once the electron is detected, how come the momentum has many possibilities? Should the momentum be that which is which it was in instant before it was detected?
Suppose this is x. And the wave function now looks like this, which means that the probability density is 0 here, the probability density is 0 here, and there is a finite realm of possibilities for x. Okay? Okay? Now delta x is not infinity. This is delta x. The realm of possibilities of where you can detect the electron is now finite. Previously in this case it was infinite. But now I have drawn a different wave function. The realm of possibilities is now finite. Now can you tell me what the momentum of this wave is? Or in other words, can you tell me what the wavelength of this wave is? No, because this wave is composed up of a large number of waves. This plus this plus a different wavelength plus a different wavelength. So there is a range of wavelengths that add up to give you this wave. Okay, this is the concept of the Fourier integral. Hence, there is no precise momentum. Rather, there is a range of wavelengths, a possibilities of wavelengths, a possibility of momenta. Okay, so if this is to squeeze, if delta x is to reduce, the range of possibilities of the momentum has to go up. Let me remind you of what we learnt in the Fourier integral. The Fourier integral is now going to make sense to you. Therefore, I remind you that you'll be better off at the end of this course than you were at the beginning, because things come cumulatively, they come up in steps, gradually. K, Fk, K, K, now I am calling this the wave function. The wave function is a function of x. Now if I take the Fourier integral of this function, I will obtain, we did this in the class, a sinc function. Now for this function, the range in x is this. The realm of possibilities or the uncertainty in x is the width of this lobe. The realm of possibilities of the momenta or the wavelength is delta k, is this much. Now how are these related? These are related by the Fourier integral. This is the Fourier integral of this. Okay? Now if I take the Fourier integral of this function, this has a reduced delta k. It has a reduced delta k, therefore this spread has to increase. So the realm of possibilities of x goes up, but the realm of possibilities of momentum goes down. And likewise here we would have something like this. So now for an object that is very narrow, extremely narrow, and I make it so narrow that I just hit this axis, the realm of possibilities of k has to increase. It has to go to infinity. Therefore, the momentum is totally uncertain. Okay, and I cannot tell what the momentum is. Likewise, in this case, I can tell what the momentum is precisely, but I cannot tell what the position x is. Okay, so x and k, they are like seesaw variables. More questions? Please raise your hands. आप पूछें?
So when you ask the question, where is the electron? This question presumes the electron is a particle, because only particles have position. How can the electron have a position if it exists over all of space as a field?
Right. Which means that this question is really not a legitimate question as far as quantum mechanics is concerned. Where possibly the electron could be found is a legitimate question. More questions? आप पूछे? Which case? Right. This one? Because how do I construct this wave function? I construct this wave function by adding many functions of this kind, of different wavelengths. Okay, so if I were to measure the wavelength of this function, I could either measure this wavelength or this wavelength or this wavelength or this wavelength. I have a range of possibilities for the wavelength. Okay, if I were to measure the position of this particle, I have this range. If I measure the wavelengths, I could measure either this wavelength or this wavelength. So there is a finite range for x and a finite range for the momentum or for the wavelength. Remember, the momentum is related to the wavelength. Okay, more questions? Aap पूछे.
After we have two cameramans which are observing the same space, at the very same time.
One electron. There's only one electron.
One electron.
Mm-hmm.
So is it possible that the two cameras observe different position of electron at the same time?
See, can anyone answer this question? Does anyone understand the question?
Sir, at the same point in time, the same point in x.
Very possibility. Both the cameramen will detect the electron at the same position at the same point in time. If both of them turn on their cameras coincidentally, both of them will measure the electron at the same point in space. कौन लोग इसमें believe करते हैं? बिल्कुल गलत है ये जवाब। उसकी वजह ये है कि when the field of the electron collapses, it acts like a particle, and that particle can be registered only on one camera. So if one camera detects the electron and says, Viola, I've seen the electron, the other cameraman will have a droop face because he will not see the electron. The electron has collapsed onto one position, onto one camera, and the electron as a particle, it cannot be split. Second possibility, therefore only one camera will flash at a time, and that answers your question. Now, before we break for the class, I have a request from a student, and one of our students would like to come here and address you for a couple of minutes.
Hello everyone. Just before the class starts, we just want to give a little message to you guys. As you would know, the student council elections are coming up. The date is 23rd April.
Not anyone, so.
But you see, many people in UMS will say that the student council is pretty much useless, it doesn't do anything much. But that's not true. Because you see, in your 4 years at UMS, there will come a time when you will have to wrestle with the administration. A time in which you will be carrying signed documents, taking from one office to the other. And at that time, you will need help. So for that, ladies and gentlemen, I present one of the most helpful and liveliest students of our batch, co-founder at the Lounge 409, Mercy.
I'm Umar and I'm running for the student council elections on behalf of SSC. यार आज मैं आप लोगों के सामने खुद इसलिए आया हूँ ताकि मैं पर्सनली आप लोगों के वोट मांग सकूँ आप लोगों से।